Hi, my name is Robert Stahulak, and today I will be talking about the work that I've been doing to improve calculations of the nuclear equation of state, specifically looking at increasing the efficiency of the calculating high-order quantum contributions to that equation of state. So, what is the nuclear equation of state, and how do we use it? Like any equation of state, the nuclear equation of state relates different state variables of a state of matter. Typically for the nuclear equation of state, we look at just energy density and pressure, as these are the most useful quantities in most of the applications that we look at. And it's useful whenever we can consider a large group of nucleons together. So typical examples of that are neutron stars, supernovae simulations, and sometimes we look at heavy nuclei as well. Neutron stars is the most common application, as neutron stars are essentially giant nuclei with the mass of a typical star. And in order to calculate the size and structure of a neutron star, we almost always need an equation of state for the nuclear matter. One typical way that neutron star structures are calculated is using the TOV equations, which I have here on this slide. These are essentially hydrostatic equilibrium equations defining the conditions of all of the matter inside that star such that it will neither collapse nor expand, which is how we view most stars that exist. And by using the equation of state, we can relate some of the unknown variables in these equations. So here rho is just the nucleon density, P is the pressure, and if we just have an equation which easily relates those two, we can numerically solve these differential equations and just build the structure of the neutron star outwards from the center using numerical techniques and totally solve for the structure of the neutron star. Neutron star astrophysics is a pretty popular area of research right now. Techniques like this, though more sophisticated, will be increasingly relevant, and of course we'll be needing the equation of state. Okay, so then how does one actually produce the nuclear equation of state? So there's many different ways, but almost all of them rely on quantum many-body theory. In particular, the ways that we look at are doing a perturbation theory expansion, calculating a approximate Lagrangian, which I won't go too much into, but this process involves looking at all of the different ways that the nucleons can interact amongst each other. So evaluating different possible modes or pathways of those interactions. The figure I have on the right here just shows sort of the most general examples of how those interactions might look. Dotted lines are exchanged particles, and the vertical lines are actual nucleons involved. In this expansion, we calculate many different orders where as we go to higher and higher order, we're looking at higher order Feynman diagrams, more complicated interactions. So as you go down this diagram, you look at more complicated interactions where we might see 3 nucleons interacting, or even 4 as we go higher. Typically, this calculation is cut off before 4 nucleon interactions come in. So at an order next to leading order, so the green there, where most of the contributions to the equation of state have been taken into account. And terms further than that are taken just as usually an error estimate. So in actually calculating each of the terms in this expansion, that's not so simple, as each of these interactions must also be summed over all of the possible states for the particles that are involved. So that includes, for each particle involved, a spin, isospin, basically proton or neutron, as well as possible momentum or energy states. And these sums can be quite computationally extensive and take quite a lot of computing time. And especially if simplifications are not done, as they are actually typically not, just due to the complexity of doing those simplifications before just tossing it into the supercomputer. So the typical way of doing these sums is just doing a numerical integration for the momentum states, but just throwing the summation over possible spin and isospin states into that integration as well, which sort of multiplies the degrees of freedom and makes the integration much more complicated and take much longer. So this is not actually necessary, as I have this little point here that those sums can actually be decoupled, and the spin and isospin sums can be done analytically first, simplifying the whole thing, though this is quite a tedious process to do by hand. So just to sort of summarize, calculating the nuclear equation of state requires a large number of sums and numerical integrations with a very complex integrands, and the numerical integrations are usually the most time-consuming part, especially when we're sort of tossing the spin and isospin sums in there together and doing them all at the same time, as is currently usually done. So then the goal of my research is basically just to create an automatic way of performing these spin and isospin sums analytically so that they can be actually just compiled and reviewed beforehand and then passed to various numerical integration techniques. And through this, hopefully the overall calculation can be made much more efficient, much more quick. And I'll be doing that just by building a set of tools to do a very large number of symbolic and matrix algebra calculations quickly in order to analytically treat all of these different possible interactions over the different spin and isospin states. There's also sort of a more minor possible application, just that if this can be made much more efficient, we can take these calculations in the perturbation expansion to higher orders, more complicated Feynman diagrams, just because, well, we can if things get a lot faster. Just by design, usually those terms contribute less, and so nothing major is expected to be discovered, but it would be important just to verify that we know how these different interactions contribute to the equation of state overall. Okay, and that's